Okay, we are live. So, Danuta, first, again, thank you for your inviting to present one part of your work. So, Danuta Wisniewska, I thought this is the right pronunciation of your last name, but Danuta is graduated in português. Danuta é graduada em Biologia Marinha na Universidade de Gdansk, na Polônia. Fez doutorado na Universidade Aarhus, na Dinamarca, onde também continuou por mais de 4 anos, fazendo seu pós-doutorado, onde estudou ecolocalização e comportamento de forrageamento de harbor porpoise. Em seguida, passou 1 ano em Stanford, nos Estados Unidos, trabalhando no pós-doc com cinemática e bioenergética de cetáceos. Em seguida, passou mais 5 anos no Centro Nacional de Research and Scientifique, na França, no seu 3º pós-doutorado, e agora, no 4º pós-doutorado, no 3º pós-doutorado trabalhou com decisão de forrageamento e interação social de pinguins, e agora, no 4º pós-doutorado, está trabalhando no Sound Communication and Behavior Group, da University of Denmark, na Dinamarca, com ecolocalização de morcegos, que é parte do trabalho que ela vai apresentar hoje. Danuta, thank you again for accepting our inviting. So you have around 1 hour, so it's your time now.
Thank you as well, and thank you for inviting me to give this talk and for bringing some understanding when I had to cancel due to illness a few weeks ago. In the meantime, as I told you, I've got COVID and I'm still recovering. So if I apologize if I sound a little bit hoarse, and if at any point I become hard to understand, please feel free to interrupt me. As I guess Israel has mentioned, or maybe did not mention that I met him and Rodrigo when I joined British Well fieldwork in Cabo Frio last year. And I think he's mentioned that most of our research so far has focused on echolocation, foraging ecology, and energetics of whales. But 2 years, I joined a bat echolocation lab at the Sound Communication and Behavior Group of University of Southern Denmark. And Israel asked me to talk about what we've been up to in the lab. Since it's part of a course in ecology and evolution, and my understanding is that people come from different backgrounds, not necessarily bioacoustics, I thought I would start by providing some information on the evolution of echolocation in bats and how it functions in these animals. Bats are the second most specious group of mammals, surpassed only by rodents, and comprising more than 20% of the mammalian species diversity today. They can be found on nearly every part of the planet, except in extreme deserts and polar regions. And according to the IUCN Red List, Brazil alone is home to 167 species of bats that inhabit a variety of biomes, including Amazon rainforest, Atlantic rainforest, Pantanal, Cerrado, and Caatinga. Bats come in many shapes and sizes, as appreciated amongst others by Haeckel in his famous book. They occupy variety of habitats and emit sounds through their mouths and or their nostrils. They feed on insects, nectar, fruit, blood, as well as other small animals like lizards, frogs, fish, rodents, and birds. The global expansion of bat species, which represents one of the greatest adaptive radiation in mammalian history, is largely attributed to their ability of power at flight and echolocation, of course, which enabled them to conquer the night sky, a vast and, at that point, unoccupied ecological niche. Bats first popped up in fossil records around 55 million years ago, but the fact that they were small animals with fragile bones and likely inhabited forested areas that did not offer good conditions for the formation and preservation of fossils make bat fossils rarefied. And so the exact evolution path that bats took is still a puzzle. Well, there's a general consensus that bats that parrot flight evolved in bats only once, where their echolocation in bats has had a single origin or evolved multiple times independently, is still debated. Long before the discovery of echolocation, bats were, based on morphological data, bats were divided into two suborders: the Megachiroptera or megabats and Microchiroptera, which were further split into Echinochiroptera and younger Chiroptera based on the morphology of their jaws. Megabats were all members of a single family, the Theropodidae, commonly known as the Old World fruitbats or fly foxes, while microbats comprise the remaining bat families. And since flying foxes do not echolocate, except maybe for 6 or 7 species which use tongue clicks to navigate in caves, and all microbats reported so far do echolocate, for many years the prevailing hypothesis was that echolocation evolved once in the common ancestor of Echinochiroptera and Echinochiroptera. However, with the advancement of molecular methods, phylogenetic studies starting in the 80s provide more and more evidence for the microbats being parallel than monophyletic, with the rhinolophoid bats, marked in green here, being more closely related to the fly foxes than to the younger Chiropteran bats. And so the micro and megabat division was dropped, and currently bats are divided into Echinochiroptera and young Chiroptera. What does it mean for echolocation, for evolution of echolocation? Two scenarios are plausible. One, larger echolocation evolved multiple times independently in the lineages of bats. Another scenario would be that larger echolocation had a single origin and was subsequently lost in flying foxes, in the theropodids. Up until recently, most studies seem to provide more support, evidence to support the single origin hypothesis. However, a study that used extensive biological data and was published last year by Nodiri et al. Seems to be tipping the scale more towards independent origins. So the debate continues. I'm not going to go into detail on echolocation fold design in bats, since the diversity of bat shapes and sizes is pretty much reflected in the diversity of bat calls. So it's a lot of ground to cover. I just wanted to mention that bat signals can be divided into several categories, and that the categories are in most cases represented in species of both the Echinochiroptera and the younger Chiroptera, which suggests that the animal's ecology and the perceptual challenges imposed by the environment in which the animals live may be more important in shaping call design than their evolutionary history. All right, let's move on to how echolocation actually works. Echolocation, or by sonar, is a deceptively simple sense. An echolocating animal emits a sound signal that bounces off objects in the environment, and the returning echoes carry information about the objects back to the animal. Once a bat detects a target, the primary task it has to perform is target localization and classification. To localize an object in 3D space, a bat has to estimate its distance, azimuth, and elevation. How does bat do that? Well, it estimates the range to target using echo delay and the speed of sound. For azimuth and elevation, bats utilize their binaural hearing, interoral differences in sound level and arrival time, provide information on azimuth, while the pin-induced modification in the spectrum, in the sound frequency spectrum, provides information on elevation. In terms of classification or discrimination, target size is estimated from echo level and duration, whereas its detailed properties are estimated from the time frequency structure of the echo. And bats are really good at performing these tasks. I have to mention that this video was recorded with infrared lighting that's invisible to bats. And so this bat operated in complete darkness. Let's watch the video again, but this time at its actual speed and not slowed down. That was it. And here's how a bat-inspired robot, a so-called SLAM, performs a similar task. SLAM stands for simultaneous localization and mapping, and it's about a robot inspired by a robot built to mimic the abilities of bat. It has a single emitter and 2 receivers, and it relies on echolocation to navigate through an evolving environment. So using echoes returning from the environment, but the robot delineates a border around the objects in the environment and uses, we'll stop it for a minute. So it uses echoes like a bat to localize the targets, limit its borders, and then it classifies the objects using a natural neural network to then create a map like you saw in the video earlier, a map of the environment. The robot can also use the classification to decide how to interact with the objects in its vicinity, in its immediate vicinity. So here, for example, you have a soft plant versus an actual barrier that an animal cannot move through, and the robot decides to go through the soft plants. The performance of the robot is quite impressive, but it's also painfully slow. And that's because of the acoustic processing being so complex and time-consuming. Human echolocators are a bit faster, but they are still way behind that. So why are there such large differences? Well, first of all, millions of years of evolution, but sound production is adapted for echolocation. The larynx is larger and ossifies earlier in the development than in other mammals. And the mouth cavity and nasal passages are adapted to filter the sounds to optimize them for echolocation. But hearing is also adapted for echolocation. While bats have the same hearing threshold as other mammals, their outer ears are larger, their high-frequency hearing is better, and their auditory brain ranges are enlarged in bats. But there's one more reason why bats perform so well and are so fast, and that's that, like many other animals, bats cheat. Echolocation is an active sensory system, and that means that bats utilize energy that they themselves produce, but also have control over. As bats navigate through the environment, search for and track prey, they adapt their echolocation calls to the context in which they operate. So first of all, bats don't like call overlap because that would lead to ambiguity where the returning echoes cannot be reliably matched up with the source calls. And so bats will wait for echoes to return before they emit another call. They may also use differently structured signals when they perform different tasks and operate in different environments. So here are examples of calls recorded from two species of bats, an open environment and in dense vegetation, and also when they perform different tasks. And as you can see, in open environment bats, both species produce long and narrow band signals, and those signals fit a lot of energy, and so they're good for detection in open environments. However, in flat-rich spaces, in dense vegetation, bats switch to shorter signals and more broadband signals, and that's because those help them avoid overlap with echoes returning from nearby objects, and broadband signals are also better suited for target localization. Similarly, bats adapt the structure of their calls as well as the rate and levels at which the calls are emitted when searching for approaching and tracking prey targets. As bats close in on targets, get closer and closer, the echoes return with shorter delays, and therefore bats emit shorter calls, again to avoid call-like overlap. They emit them also at higher rates to maximize the update rates on the target position. At the same time, bats decrease the level of their signals. Now, signal source level and duration determine the amount of energy in the signal, and that will eventually translate into the strength of the echo for a given target at a given distance. So a target's distance is determined by the echo strength or echo level being greater than the hearing threshold of the animal. And so a sonar range is basically defined by sonar range for a given target is basically defined by the amount of energy that the bat is emitting. In other words, for a given target, or a given target can be detected by a bat at longer ranges if the bat produces louder signals or longer signals. And so, based on the data to the left, this plot was created to basically illustrate what I've just said. Here you can see that when the bat is more than 2 meters from the target, it probably hasn't found it yet, and basically searches or echolocates with a range that would allow to detect the target if it was within 2 meters of it, or slightly more than 2 meters. So if the target was within the blue space here, it would have been detected. Once the bat detects the target, it zooms in, it adjusts its level and duration. And so when it's around 1 meter from the target, it overshoots a little bit, but still anything that is farther than 1/2 meter from the bat or 1/2 meter behind the target will not yield audible echoes. And so the space here that is marked here is objects in the area that do not yield audible echoes. Everything that is there will not be detected by the bat. In this way, essentially what the bat is achieving is sensory match filtering. Bats are extracting the most crucial and relevant sensory stimuli or information while suppressing or even rejecting other stimuli. Other examples of such filtering that are maybe more familiar to us are formed by our eyes and ears, which detect only a subset of the wavelengths and frequencies that are available in the environment. Sensory match filtering saves the brain a lot of unnecessary computations and makes decisions faster and with saves energy. At sometimes the expense of almost making a mistake. However, basically, by reducing source level and duration of their signals, bats simplify the echo scene and filter away irrelevant information. That's basically what allows it to be so fast. Another way of filtering or simplifying an acoustic scene is by using a directional beam. Imagine you're a bat out in the environment trying to find something to eat, and you produce a call that propagates in all directions. Eventually, will hit a moth target, which will give rise to an echo. However, if the target is not alone, there are other targets, and they may not be as interesting to you. Those targets will also be hit by the sound and give rise to echoes. And there may be a lot of them. They may overlap with echoes from the target of interest and make it more difficult for you to track the target that you're actually interested in. a way to limit that is to emit your sound in a narrow cone. Since when less sound is radiated to the back and sides of the bat, less sound is reflected of objects of little interest or no interest in those directions. And this way, again, we reduce the amount of information, or the bat reduces the amount of information it has to process. Another advantage of directional beam is that it simplifies the localization task, because basically only the bat emits the bat only has to localize targets that are actually within the beam. Yet another advantage of a directional beam is an increase in source level or on-axis intensity. By focusing energy in a narrow cone instead of radiating it in all directions, the energy can reach farther. The amount of such gain or level gain is usually estimated with a directional index or the activity index, DI. DI compares the emitted source level of a given emitter with that of an unidirectional source that produces a signal with the same amount of energy. In other words, here you can see that DI in most cases around 12 decibels, and that means that if a target that if you record at a given distance, say 1 meter from the bat, the level you record will be 12 dB higher than it would be if the bat emitted the energy in all directions. Directionality increases with the signal frequency and emitter size. So, in principle, bats of different sizes can converge on sonar beam patterns by adjusting the emitted frequency to their size. And small bats can achieve the same directionality as larger bats by using high frequencies. And that's actually what has been recorded and what that plot that you see before shows. There are bats recorded from many different families, and that what shows that most bats, that the activity index of calls of most bats seems to oscillate around 12 dB. So there seems to be, so directionality seems to be a feature that is of quite high importance to the bat echolocation system. But directional beam may also come at a cost. It does restrict the bat's field of view. In certain stations, it might be disadvantages. So imagine again, you're out at night looking for mobs. You detect one and you get closer and closer. As you since your beam is narrow, at some point it becomes very easy for a mob to escape your beam. One solution to that would be to widen your beam, of course. Where bats do that? Well, back to the plot from before. One property of the calls that I haven't discussed, haven't mentioned before, is frequency. As you hopefully remember, there's a relation between emitter size and signal frequency, and so one way that bats could be making their beams less directional or wider would be to decrease their frequency, and that's what as you can see, bats seem to be doing when they go into that final approach, that final part of target tracking. I'll just play this out. Will you hear it? Maybe not.
No, it's not playing.
It's not playing. No, sorry. Well, you then have to believe me that the frequency that the calls decrease in level, and you can see that they are emitted more frequently, and that their frequency drops. And that actually has been confirmed by array measurements that showed that beam becomes significantly wider in that last part of the approach when animals are closing in on their targets. So to just recap, the bat's ability to filter echo information is crucial to their speed and accuracy. That helps them perform the tasks of echolocation more efficiently and faster. A beam shape is a spatial filter that determines what information is available to the bat and what information is filtered out before echoes return. But just beam shape and filter information to suit the environment and filter other information or filter the information that they receive from the environment to suit the context, the environmental and behavioral context, by adjusting the duration, emission rate, source level, and frequency, and sometimes emitter size of the emitted cause. Just FYI, is to throw in some whales and more convergent evolution. Whales did definitely evolve echolocation independently of bats, but they have converged on personal behavior where they emit echolocation signals at a higher rate, lower levels, and with a wider beam as they approach their targets. So that's what bats do on the emitter size. What about the receiving? What about on the receiving part? Well, but hearing is also directional, I'm going to go a little bit more into those slides later, but basically the most direct way of studying the spatial cues that are generated by outer ears and that are available to animals is by considering head-related transfer functions or RTF of bats, and that's basically what these plots are representing. Again, you have azimuth and elevation, and the lighter the color here, the more energy is coming from that particular direction. So you can see that, like a beam, directionality of the emitted beam, directionality of the received beam also increases with frequency. So there's the energy is coming through a narrower cone. The HRTF has traditionally been measured by fitting a microphone into the ear canal of a dead bat. And then the bat is put into an anechoic chamber, and a series of microphones are put or a moving microphone is usually playing sounds from that cover a sphere around the bat. You may be more familiar with the way that's done in humans, especially now that 3D headphone or headphones that are capable of playing 3D sounds become more and more popular for gaming, I guess. So that's basically the same thing, just shown animated. So there's a human subject in an anechoic chamber, and there's a series of microphones that play sounds at different frequencies around that move around the person, and microphones in its ear then record how the sound is modified by the head and the earlobes of the person, and in this way you can customize basically. Or you record how individuals' ears and head properties modify the sound that a person is experiencing. It's the same way that has been done in bats, just with heads of the bats and microphones placed in their ears. And as I mentioned before, you have the directionality here in the middle. that increase of frequency, that's the same for emission. And then you can see that a combined pattern. And so both the emission and the directionality of both the emitted signals and directionality of the ears contribute to what the bats are eventually experiencing. That has been done in several studies, and so several bats. And all these studies suggest that sensory match filtering in echolocating bats depends both on the emitted and the received beam shape. However, as I mentioned, the existing knowledge on the received beam is all from dead or stationary animals. Actually, more and more popularity, or I forgot to mention that there's more and more studies that use micro CT scans and acoustic modeling to get at basically the same patterns, but then you still require a bat to be stationary, usually under anesthesia to perform the CT scan. And we know that most bats are capable of moving and deforming the ears. That's the same bat. I hope this video is working. So that's the bat that you saw on the first slide, along your brown along your bat. You can see that when it's playing, it has its ears upright. But when you first actually catch a bat like that, when it wakes up, the ears are completely folded. And that's the same for other bats, at least the ones that I've worked with. They are capable of, so bats are moving the ears, and they are capable of deforming them and move them. So to fully understand the spatial filtering that bat ears provide, it is crucial to know how those ears are oriented when bats are performing realistic when bats are in realistic echolocation scenarios, when they are performing actual echolocation tasks. And that's what our group has set out to do, or set out to do a couple of years ago. Starters, we wanted to answer 3 questions. What is the receiving beam shape in free-flying bats? Do bats dynamically adjust their receiving beam as they approach targets to suit the context? And how does the combined effect of the emitted and received beam dictate the sensory match filtering in free-flying flying bats? And now, there's a good reason why this has not been measured in free-flying bats before. You've seen how fast and maneuverable the animals are. You've seen a bat catch a moth, and so to make it possible and to slow the bats down, we've had the university built as a big wind tunnel. The wind tunnel is around the university. It's built of a set of containers, and which has basically a fan and it's a closed loop system, and it has a fan one end and a test section with an office section in the middle. So that's a picture taken in the section, obviously with light. Normally it's completely dark, and there's a lot of infrared cameras, infrared lights everywhere. In the test section, we have a grid of strings to which they are attached microphones. We have a microphone array of currently 21 microphones. Those microphones are recording at high rates. It's 375 kilohertz, and they are synchronized with 2 high-speed cameras that we record with at 2,000 frames per second. There's a lot of strong red lights, but it's still a high rate and very little light. So we have a very short focal length. And so to be able to record the bats, we train them to approach targets in a more or less straight path, and to give ourselves a chance of recording more than a single call, we blow wind at them to slow them down. And that allows us to record videos like that. That video slow down 100 times. And basically, you see that we have a prey item on carbon fiber poles, and the bats are trained to grab that. And what we're interested in is basically what the ears are doing in these situations. To do that, we are using a deep neural net. We have marked 21 landmarks on the bat's head, and we have trained a deep neural net to track those through the videos. And then since we have two synchronized cameras, we can use photogrammetry to convert the 2D data frame by frame to 3D positions. And so here's a video of what basically looks like with the points marked by the neural net, the two cameras, and on the bottom here you see ear separation. So you can see that as the bats are approaching, the ears are more stable. At some point, they go into what I call Yoda mode, when the ears go to the side. The bats really resemble a Yoda. And we can see that in those moments, the ears go down and to the side, and so the ear separation increases. If we combine the data from the camera and the microphones, we see that what happens is that the ears start changing direction when the bat is going into the bus, and which means it's starting to close in on the target. And we recorded four individuals of this species, and we plot all the sessions for those animals. We see that that's a general pattern. So it seems that the ear motion is matched to the acoustic behavior of animals. I mentioned the head-related transfer function. We also measured that on that individual of the species to get at what those changes we observe mean to the animal. So here, the darker or more red the color, the more energy is entering from that particular location, or the more energy the bat is receiving from that particular location. And that is basically what happens. That's the right ear, and that is basically what happens when the bats move them. The ear gets separated, and the area covered in this way, they are covered by the ears, gets larger. And so there's still no more analysis to do, but our preliminary conclusion is that the receiving beam is markedly different in free-flying bats than in stationary dead bats. And that the receiving beam is adjusted dynamically during prey pursuits, same way that and in synchrony with the adjustments made to the emitted beam. And so what we are focusing on now, or the work that we're doing right now, is more analysis. We still have to combine the emitted and receiving beams. We have to combine the beams from both ears. We are recording more species that including those coming from different niches. This year we have been recording bats that troll prey from water, and two species of cryptic bats present in Denmark. Bats that look the same but use different frequencies, and that's how they are usually recognized. And spoiler is that we see the same thing, the same pattern. They all, even though they come from different genus, and hunt in different ways. They all adapt their ear position as they close in on targets. What we are also working on right now is a setup that allows us to move prey, and so the next step will be to move the prey randomly as the bats are closing on it, and see whether and how the bats react to it, whether they move their ears to follow that. Another way that path or another analysis that we're doing is trying to get at the head rate transfer function of live bats, and we try to do that using a 3D photogrammetry models, or creating 3D models with photogrammetry and combine that with acoustic modeling. And so the way to do that right now, the way we do it is take a lot of pictures, align them, a lot of pictures from many different angles, align them, and then build dense clouds and mesh, and then add texture, and basically we arrive at the same object that we hopefully arrive at the same object that we scan. We can then use that model the same way as CT scans or micro CT scans are used for acoustic modeling to get at the head rate transfer function of live bats. Where we are at right now is basically testing the setup. We have currently we have 10 synchronous cameras and a turntable that rotates the bat or a bat head, and we have three strobe lights. The test that we are performing right now is basically with a 3D printout from a CT scan, and the idea is to apply our methods and acoustic modeling, and then apply the same modeling to the actual CT scan and see whether there are differences between those, and whether those two methods can be used interchangeably. Our plan is to possibly go up to 40 cameras, and the advantage of this method will be to the reason why we want to go to 40 cameras is so that we don't have to use a turntable and can take all the angles or pictures from all the angles at the same time, so that because the bats are moving and we do want an active bat when we do that. This hopefully will allow us to do what is basically do what is done to with those human HRTF that are individualized, so that we can actually have the HRTF of those animals that we work with without the need to possibly compromise them by putting under anesthesia or killing them. And so the idea is to use that method in combination with our camera and acoustic recordings, and we also hope to be able to make the system semi-portable, so we can also take it in the field and work with wild bats, possibly in other areas, not only in Denmark. So that's where we are at right now, and I would like to mention the members of my lab that are involved in this project, and so my co-authors, Lasse Jacobsen, who is the head of the lab and who's done most of the work on the spatial filtering and beam adjustments of bats. while I was working on the same problems in Wales. Felix is a PhD student on the project, and Karsten is a postdoc who's mostly working on the photogrammetry method and the acoustic modeling. He's an acoustic engineer. And so I would like to thank you for your attention, and we'll take any questions.
Thank you so much, Danuta, for your presentation. It was awesome. Solve these results, or well, actually, it's part of the results of your project. It's an incredible enforcement to understand how they behave or doing flight, I think. We already have some questions on YouTube, but first we open for some questions for the audience here on Zoom. So, alguém tem alguma pergunta para começar? Se não, eu passo para a pergunta do YouTube.
Opa, eu gostaria de perguntar um negócio.
Ok, pode perguntar.
Sorry, my English is a bit rusty, but I will try.
No worries.
A few months ago, I was studying about bat evolution in general for a scientific communication project that my lab has. And I was reading that the evolution of echolocation came after the development of the flight capability of the bats.
Yes, I mean the oldest known fossil, as far as I know, did not show the adaptations to the inner ears that are required to use at least the advanced form of echolocation. So they could have used a very rudimentary form of echolocation, but not at the level that bats are using echolocation right now.
Yeah, exactly what I was thinking. You said there was some difference between the static bats and the moving bats. No? I remember that when I read this at first, the first thing that I saw was also that it was too energetically costly for the animal for this.
Yes, it is. So that's another thing that bats, as I mentioned, is that flight really makes echolocation cheaper for bats, and that they to a large degree synchronize their calls with the flaps of their wings, and in that way they use less energy to produce that signal. Yes.
Amazing. Yeah.
Yes, it's an amazing system. And I think the incredible thing is that there's so many species that do so many different things, and there's still so much not known. For most of the species, we don't even know if they're emitting their sounds through their nose or their mouths. I mean, there are some obvious ones, of course. Those bats that have incredible nose leaves are most likely nose emitters. But the bat that I had on the first picture, the long-eared brown bat, it doesn't have a nose leaf, and it's still a nose emitter. And so there's still a lot we don't know, and I think the fact that there's such a variety and so many species to work with make also the phylogenetic studies so much better than for the system I come from the Wales.
Incredible.
Thank you for a question, Tel. It's one of the students of the discipline of this course. So I think it as the same subject, I will take one of the questions from YouTube from Felipe Maurin. So Felipe asked you mentioned that bats are very plastic regarding of echolocation and distinct environment. When this plasticity emerges in evolutionary time scale?
I don't know. We actually don't know because it seems like it's adaptive radiation is an ongoing process. One of the projects that I did mention that we are working on right now is those cryptic species. We have two species of bats in Denmark that basically look the same, and for a very long time they were considered a single species. at some point, people discovered that those species were that there are certain groups of those bats that don't mix, they don't roost together, and they use the signals that are offset by 10 kilohertz. And so people thought, okay, these are those two different forms of the same species. But when finally molecular methods were applied to these, it turns out that there are two different species, and the acoustics is actually used to identify those. We still know exactly what drove that, what drives that difference in their echolocation, that the ecosystem is so different. They are the same size. And so what we're trying to work with in the lab right now is to record those and look at their directionality, where there are consequences of those 10 kilohertz to their beam directionality, or whether they compensate that with their mouths, because what we think right now is the most plausible explanation is that their jaws are different. That one of the species has slightly different jaw size and teeth, and that is due to an adaptation to different prey. So they go for different prey, and that has consequences to their beams, because the emitter size drives the beam, and so to correct for that, those two species switch to different frequencies. And that is something that happened quite recently. So I think it's very hard to that's a long answer to your questions, but yeah, we don't know. We know that bats that were around 50, whose fossil records are from around 50 million years ago, probably already used echolocation, and that there are fossils that seem to show different or bats that use different or use echolocation differently. And so that happened already millions of years ago, but I think it's an ongoing process.
Okay. He sent another question here asking about the species that use echolocation. Does some species there are more plastic than older among the species that are used echolocations? I think he thinking about if echolocation make the species more plastic.
Yes.
Or like
yes. So there are some species that the bats that I haven't worked with, and the part I talked about that are thought to use the most advanced form of echolocation are the bats that use Doppler compensation in their signals, and those bats used Burr stereotyped calls. So actually, the bats that use less advanced echolocation, the ones that we work with, modify their signals way more. They have more, I guess, material to work with. Again, there's thousands of species of bats, so it's hard for me to say. Most of them are vespertilionid. A lot of them show this flexibility. I cannot tell which ones are the most the most flexible.
Okay. Another question here from the audience on Zoom. Mais alguma pergunta aqui no Zoom, pessoal? Alguém quer fazer mais alguma pergunta para a Danuta?
Yes.
Okay.
Can I? It's only a curiosity
about
the benthic marine echolocations. If you have some news about this, or
about
marine systems.
Yes.
With turtles or benthic ones, and like corals or mollusks, arthropods. Do you know something about this?
Whether there are other animals underwater than whales that echolocate?
Yes, underwater, the benthic organism.
No, not that I know. I mean, there can be, for example, like amongst whales, only toothed whales are known to use. Toothed whales are used to are used like advanced form of echolocation. It's again as I mentioned in air, there are some species that like some species of megabats. There are some species of birds like oil birds, shrews, humans that use some form of like rudimentary form of echolocation to navigate, to move through their environment, and probably whales. Baleen whales may use that too, to some scale, for navigation, for obstacle avoidance, but not in the way that bats and toothed whales are using echolocation, where they can detect incredible detail and differences in targets and identify and track prey. So to my knowledge, these are the only two groups of animals that use this form of echolocation, this advanced form of echolocation.
Okay.
There's some report for humans that blind people that use echolocation to
yes. Yes, and I met Daniel Kish, who's probably one of the most famous person, and I encourage you to watch his TED Talks. It is incredible what he can do. He can tell the shape of he can tell that there's a building a few hundred meters away or closer. That this is a car. That he can tell the shape of the target, and so it's something that with experience you can learn, and you yourself here. Like if you just put a book in front of you and make a sound or a plate or a piece of metal, you will hear the differences. There've also been experiments with human divers that were exposed to echoes underwater from different materials, and humans can identify it. I mean, you will be able to identify it. So there is something that you can learn and use to some degree, but again, we're going to be probably a little bit better than that robot, but we're not going to use it the way that bats or toothed whales are able to use it.
Okay, thank you very much.
Great. Nice. I doesn't know about this with humans on the water, but it's incredible.
Yes, it's an experiment that was done with U.S. Navy divers, of course, probably in the 60s or 70s. A lot of the whale literature actually was traditionally made was focused on the abilities of whale sonar but a very artificial abilities, like experiments with target discrimination, size discrimination, material discrimination, the thickness of walls of different targets, what detection ranges, and so on, because the interest was mostly from Navy, and only the last probably 15 years. The whale sonar research has focused more on the ecology and actually on what the sonar does to or provides to the whales. Whereas with bats, the research was more focused on the ecology, but very little. There were very few studies that focus on the physics and the properties of bat sonar, like the directionality, for example. And so that exchange of knowledge, so that's those techniques like microphone arrays to measure directionality, and now acoustic tags are just now being used, and in the last 10-15 years being used in bats. Whereas in whales, they've been used for decades, and vice versa. People are now, with the advancements of technology, like tags, for example, we are able to record more of whale behavior in the field, and can make similar studies that were done on bats on the ecology of bats previously. So it's a fun synergy, actually. I learned, yes. I thought during my PhD, that's basically was my goal. I saw what was done with bats, and I really wanted to try to do it with whales and learn how echolocation is actually used by whales, not to detect metal targets, but to actually track prey.
Okay, so I have a question also. When you show your data from the shape of the Earth when the bats are flying, try to get the prey.
Yeah.
I if I remember good, when the bats were flying, the shape of the Earth changed, even when the bats were far from the prey. So the shape are changed because they are trying to adapt the receiver, or because of the wing are shaking and move the air or something.
So there is a little bit of wiggle. There is a little bit of wiggle when they go, and that is something that we have to we don't know yet. We've seen it. Yes, you're very. It's a good observation. We have to quantify it and see whether that happens systematically or whether it's something that could just be the wind. I did not extract the video, but we actually have a very fun video recorded with one of the bats, with our bats this year, where the bat was pretty bad at getting the worm off the stick, and so, but it was very stubborn, so it kept going for it. The thing is that it's a very thin carbon fiber pole, so when the bat hits it, it basically moves back and forth, and that's what happened. And when the bat approached, and actually, what we saw was that the bat was kind of tracking that movement like a little antenna. So again, that is not something we have an N of 1 in that situation. So that's why we want to use a moving target, and so that we can actually manipulate the conditions of the bats a little bit better. And then I will have an answer for you.
Okay, but during when the bats are exactly catching the prey, you are focused on the position of the Earth.
Yes.
You can, in that moment, you can separate what will be intentionally produced by the bat, or would be produced by the movement of the body that change the position of the Earth.
So we were worried about it because for a moment we thought, well, maybe it's kind of like a passive consequence of a byproduct of the bat holding its membrane to catch it, and so it kind of folds its body and the ears kind of follow it. But what we also see, which was not as on the video, is that as soon as the bats catch that and that worm, and the worm is often still in the membrane, so the body is still folded, the ears go up. So they are definitely able to make those motions independently. And we also see them like when you if you see on the picture here, that's a bat that I just grabbed, and it was asleep. And it's still kind of just warming up, and so the ears, when they rest, when they sleep, the ears are to the side, and then when they warm up, the ears go up and they wiggle them a little bit and they move them, so they actually are able to move to do a lot with the ears. And the most extreme example that I've seen was actually the one that I've shown with the long-eared bat. That we actually had in the lab because I grabbed one in the hibernaculum accidentally because I didn't have much experience with bats, and I was told that the species we were going for had larger ear than the species we had before, but pointy ears. And so I saw those pointy ears, and I grabbed that in the crevice, and I grabbed that bat out of it, and then those big things suddenly appeared. Turns out that was the tragus, actually. The tragus of the bats is so big that it's bigger than the ears of these bats, so yeah, we woke that bat up and we had to feed it before we could return to hibernaculum. But yeah, they are able to move their ears quite a lot.
Okay, great. So Maria-Alice, you want to ask something?
Yes, Danuta, thank you so much for your very, very amazing talk. Lots of things, new things for us to learn about the bats. They are really amazing animals. And I was thinking when we are talking about this echolocation, about because I work on birds, and I was thinking about the nocturnal birds that we have echolocation too. And is something similar, or is completely different way?
No, so there are oilbirds and cave swift that echolocate, and when they move through through caves. And there are some studies that they can actually avoid targets, and they actively use echolocation for navigation in dark spaces. But to my knowledge, they're not able to catch prey with their echolocation. But yeah, as I said, I think animals will use any information available to them that makes their life easier, and so they will use sound if that helps them navigate through, or and not bounce into or bump into walls. But those are big targets, not small. They won't go for insects or fruit or whatever those birds are feeding on.
Thank you.
Yeah, you're welcome.
One thing that I think now is there is some bird species that there are asymmetry. For example, coruja. Sorry, I forgot the name of coruja in English. Owls. Thank you. Owls, for example, there's asymmetry in the urge to figure out the sounds in the space in like 3 dimensions. There is something similar in bats, or.
So there are actually those bats that use Doppler shift.
Yeah.
They move their ears, and probably because the signals that they're using are really bad for localization. They move their ears independently to help that. And there's a study, and it's an amazing video actually, because they go just like that. Back and forth, back and forth. But a lot of the bats, like the long-eared bat, for example, their ears are partly fused, so they are limited like that. Again, there are so many species of bats and so many solutions that those animals came up with. So I wouldn't be surprised if not only the Doppler compensating bats were doing it, but I don't know. they are such weird creatures.
Okay, thank you. So some more questions. No? Okay. Just really see. Okay. Any more questions from here, from the audience, from YouTube? I think no, we don't have more questions. So if not, we'll be end here. So Danuta, again, thank you so much. It was amazing talk. Was amazing work that you presented here. I think it's something that probably take too much time on the field and to analyze the data and to control all the things that you want through the experiment. And it's reflect your results. That's awesome. So thank you.
Yeah, I hope that maybe next time I get to give a talk will be far away. This project is, as I said, we just started 2 years ago, and it's we started with an empty wind tunnel and a lot of issues, and needed to learn Python and machine learning and all this. And so there's a lot to it, and we are still developing the methods, but hopefully now we're at a point where we can go through different species, we can do more manipulation. It's just something that requires a lot of time to train those animals, of course, and every species is slightly different. So we have to learn about what works for one species and what works for others. It's a lot of time of recording, and of course, as you said, yes, analysis. But hopefully we'll have some more answers in a few months or years. So
it's amazing. Thank you very much. Wonderful work. Thank you.
Thank you.
So thank you again. I will end this meeting, and thank you for português. Obrigado a todo mundo que assistiu e as perguntas e participou no YouTube, e para quem vai ver depois também, obrigado, e obrigado de novo, Danuta, por participar. So, bye guys, thank you.
Thank you, Zala.
Thank you.
Danuta.
Bye.
Bye.
Nice to meet you too.